from the University of Tennessee at Chattanooga in the United States. It's my first time in Dubai. Thank you so much for number one, having such a great conference for everybody to attend. Number two, coming to this talk. Thank you for being willing to spend some time learning about a new technology. I'd like to spend just a couple of minutes talking about innovation and how innovation can change our lives. Just 46 years ago, the United States put a man on the moon in 1969. I was talking with a friend earlier who has a great interest in the U.S. space program, and I know very little about the U.S. space program other than what I've seen on television. But he was explaining to me that at the time, in 1969, there was so little data storage, digital data storage, that they couldn't take a big computer up on the rocket ships to go to the moon. So they would have to actually transmit data in real time going to the rocket ship with navigation information to get to the moon. That seems amazing to us. We have more computing power today in our telephones than they had in the rocket ships that went to the moon in 1969. Innovation is something that happens when we have to meet a need or a strong desire. The American Society of Civil Engineers recently put out a report that told us that 1 in 6 bridges in the United States is in need of replacement. 1 in 6. There are many thousands of bridges in the United States. We don't have the money at the moment to replace 1 in 6 bridges in the U.S. This got me to thinking, we have to change the way that we address our civil infrastructure, whether it's bridges or whether it's ports or whether it's roadways that are concrete or asphalt. And there are 2 real ways that we can affect sustainability. Number one, we can begin using recycled materials more and more so that the sources of the raw materials are renewable. Or number 2, we can begin to design concrete structures to last longer than they do. Concrete structures at present, in the U.S. anyway, concrete structures at present don't last nearly as long as they should or could if they were designed properly with durable concrete. I got the opportunity to begin researching colloidal nanosilicas about 4 years ago when a Chattanooga-based company asked me if I could spend some time with it. And the things that they were telling me that they thought their material could do sounded unbelievable at first. I'm a research guy, I'm skeptical. But at the same time, I knew that the only way to test for innovation and test new things is to give it some time in the laboratory, see if it works, and then go to the field, see if it works in the field. So I want to take you through a little bit of that journey today. At the time, 4 years ago, when I did a literature review to see if there was anything out there on colloidal nanosilica, there was very, very little. But now, there's several papers, probably 50 papers or so, maybe a little more, from researchers all over the world that have studied this topic. So it's something that is gaining some attention. Just as an introduction, to tell you what colloidal nanosilica is it's very, very small particles of silicon dioxide. It's an amorphous silicon dioxide, typically somewhere between 1 and 500 nanometers. They're small enough where they can remain suspended in a solution, suspended in water, and the forces of gravity actually don't cause them to fall out of that suspension. So they're very, very small. But it's not a solution. It's not like a silicate solution, which is going to be where the silicon dioxide is coupled with some metal ion of some kind. The colloidal silica the particles can actually be seen under heavy magnification. And you can see that they're spherical in nature. But they're sufficiently large enough to show differences from true solutions. The way they work in general, this is just a brief overview, is that they react in a way that is very similar to the traditional pozzolanic reaction, which many of you, if you've studied concrete, know what that is. It's where A silicon-bearing material reacts with existing calcium hydroxide to form more calcium silicate hydrate. Calcium silicate hydrate is one of the 4 main reaction products of the cement and water hydration reaction. So this secondary formation of calcium silicate hydrate can happen later. These pozzolanic additives make up things that you've probably heard of, like fly ash, silica fume, ground granulated blast furnace slag, or GGBFS slag cements. Those things all have pozzolanic reactions that are very similar to what we're going to be talking about today, the colloidal nanosilica. And we see that from the literature, we see that the colloidal silica is an excellent source of pozzolanic reactions, mainly because it doesn't really differ all that much chemically from the other pozzolans that I just mentioned. But its very, very small particle size makes it highly reactive. So it's able to really undergo some serious reactions due to the very small particle size, which we know that very small particle size equals much more surface area, etc. So we know that when concrete is first placed, it's at its greatest volume most of the time. So you have water of convenience that's there above the water that's needed for the chemical reaction hydration to take place. That water leaves, the evaporable water leaves the concrete, forming capillary voids, or capillary voids, as my Australian friends like to say. Those capillary voids are like little rivers that form as the water evaporates from the concrete. The problem is that those capillary voids can, not only are they the way that water leaves, but they're also the way that water and other contaminants can enter the concrete. We know that permeability to water has been linked to durability of concrete. It's the primary indicator of how long concrete is going to last, especially in the case of reinforced concrete. Well, when colloidal nanosilica is applied, I'm specifically speaking today about post-applied colloidal nanosilica. There's been a lot of research done on integral colloidal nanosilica that's mixed with the concrete. What I'm talking about today is a post-applied, meaning the concrete's mixed, the concrete sets, gains initial set, and then the colloidal nanosilica is added as a spray. And it can be added at various times in the life cycle. It can be added from just as initial set occurs, or it can be added many months or years later. And similar effects have been noticed. Similar positive effects have been noticed from the colloidal nanosilica addition. So in post-treated CNS, I'm going to start referring to colloidal nanosilica as CNS, okay? Because it's a lot to say. In post-treated CNS applications, the pore space filled is generally going to be that capillary pore space that I was talking about, the capillary voids that come when the water of convenience leaves the system. So as that capillary void space is filled, it's easy to imagine that a lot of the hardened properties of concrete can then be improved. So the primary filling mechanism from the literature review, the primary filling mechanism is that pozzolanic reaction we were talking about. It's taking calcium hydroxide, reacting with it, and forming more calcium silicate hydrate, which begins to fill that capillary void space. So if you think about it carefully, if you reduce the amount of void space in the concrete, then there are a lot of hardened properties that are likely to improve. We're going to take a look at those. We're going to see the effects on compressive strengths, effects on drying shrinkage, effects on permeability. We're going to take a look at corrosion modeling based on reduced permeability. And we're going to look at a case study that we did in the port of Marseille, France, on a boat dock there that the port wanted to try colloidal silica because they tried many other things to increase the durability of the concrete, and they approached us and asked if we could assist in this case study. So I want to share some compressive strength effects. These are from researchers, not me. These are previous researchers in the field. And not all of these are post-applied. Some of them are colloidal silica effect in the convention, as an integral admixture into the concrete. But the effects are the same. And you can see this great lot of researchers have all demonstrated increased compressive strength. There's some thrown in there: increased flexural strength, increased bonding strength, etc. This is just continuing. So the researchers that have shown those strength improvements by using colloidal nanosilica. These are from the laboratory, the University of Tennessee Chattanooga laboratory, as well as some other laboratories. My work was here from 2012 to 2014. 2009, I think, was mostly done at Middle Tennessee State University. And it was not me. I think Dr. Heather Brown did that work. And 2000 was done somewhere else as well. I'm not exactly sure there. But you can see that compressive strength increases with the use of a spray-applied colloidal nanosilica, ranging from 11% to 24–25%. That seems like a big range between the amount of improvement that you're getting, but you have to consider these are not all the same concrete mixes. The concrete mixes are various permeability, various porosity, various water-to-cement ratios. So one key thing to understand about a spray-applied colloidal silica is that the effectiveness or the amount of compressive strength gain that you might get is related to how permeable the concrete is to begin with. So we know that concrete varies with permeability. The primary driver of that is going to be water-to-cement ratio, but other things can also affect it, such as aggregate gradation or particle size, aggregate shape. There are many, even the mix of cementitious materials such as cement, fly ash, how those particles fit together and pack together. So all of those things can affect permeability, but typically water-to-cement ratio is looked at as one of the primary indicators of where your permeability is going to be. Here we see from 2015 the compressive strength effects from the laboratory, post-applied CNS. And it's kind of hard to read, but you can see that down here, this is a kind of a curing study where we broke several samples at various ages. And you can see that we have the control being here, and this is various applications of colloidal nanosilica. I want to switch to effects on drying shrinkage, and you may be saying to yourself, wait a minute. Okay, so it affects compressive strength. We get an increase in compressive strength, and now you're going to tell us that it also does something with drying shrinkage. Well, yeah, because remember, the primary way, or the only effect, the only really effect that the colloidal nanosilica is having is filling pore space. And filling pore space, a lot of good things happen when you close that pore space. So drying shrinkage, we know from the academic literature that colloidal nanosilica reduces drying shrinkage by quite a bit. And these are, this is a graph from a researcher named Duke in 2015. And you can see he has various percentages. These are percentages of colloidal nanosilica. This was actually not a spray applied test. This was done as an integral admixture. But you can see the control. The control is here, ordinary Portland cement at the top, and you can see the drying shrinkage and microstrain decreasing. It looks like the optimum percentage that he found was around 1.5% colloidal nanosilica. Effects on drying shrinkage from my laboratory and others show a range. 2012 to 2013 is when we did this testing. From 46% to 61% or so. This is the post-applied colloidal nanosilica. And this again is not just UTC laboratory. There were a few of these studies that were done at Middle Tennessee State concurrently. And you can see that the drying shrinkage, this was a really high water-to-cement ratio here for the control. And you can see this is, again, there was an improvement there, but it was a very high water-cement ratio mix. So that's a reason for, you have various mixes, various water-cement ratios, and that's the reason for the range. So the improvement to drying shrinkage, again, is based on the permeability of the concrete itself. So the more permeable the concrete is, then the better improvement that you're going to have to a point. I'm sure that there's concrete that is too permeable to respond well, but I haven't found it yet. So again, that's the reason for the range. Effects on permeability from the academic literature. Again, we call this, if something seems to, or is claimed to solve many, many problems, or is something that fixes all your problems, in the States we oftentimes call it snake oil. Back in the old, that comes from the Wild West days, when they were settling out in Arizona and New Mexico. There would be these settlers that would go around selling these bottles of magic potions that would cure anything that was wrong with you. As a researcher, that's one of the first things that I thought when I first heard about this. I'm going, what? Snake oil salesman coming in here telling me it's going to do all this with concrete. But again, remember, it's filling the capillary voids. So it's reducing void structure, making the concrete more dense, and it has a lot of really good effects. So when we close those capillary voids with colloidal nanosilica, it closes off that route of ingress from water and other contaminants that can get into the concrete. Logically, it follows that maybe freeze-thaw durability is also improved. There are a lot of other things that research has shown. We're only focusing on compressive strength, shrinkage, and permeability today, but there are many others that we could talk about. And these are, again, a list of researchers. Not all of these. There are some that were spray applied, some were integral colloidal nanosilica, I mentioned. These photographs are some of the best demonstrations of the closing of capillary voids that I could find. And you can see, hopefully, you can see at least this number 4 here is pore space. And you can see how much it shrunk over here after colloidal nanosilica treatment. Number 1, the area beside the number 1 here, so number 1 is CSH. The area beside the number 1 is a giant hole, and it's basically closed here. In this photograph here, you can see a giant pore space here, and it's gone. You can see the pore space here is not completely gone, but it is shrunk. This pore space is gone. So you can see that filling of capillary voids is something that you can see under scanning electron microscope. The filling capillary voids from colloidal nanosilica. Now, does it have an appearance that will jump right out at you and say, hey, that's caused from colloidal nanosilica? No, it doesn't, because the colloidal nanosilica's reaction product is the same as what normally happens in concrete. As concrete gets hard, the water and the cement react. Calcium silicate hydrate is formed. Well, the calcium silicate hydrate is the reaction product between the calcium hydroxide and the colloidal nanosilica. So when we look at it under a microscope, the key indicator is that the pore space is greatly reduced, rather than something jumping out and saying, hey, I'm caused by this colloidal nanosilica. So from laboratory testing, this is, again, University of Tennessee Chattanooga lab, as well as several others. The effects on permeability were mostly done by, in fact, all of these were a test method called AASHTO T259, which is the chloride ponding test. Some of these were run, depending on the mix, some of them were run for 90 days. Some of them were run for 120 days, and in one case, out to 365 days, to show the changes. And this is just a chloride diffusion coefficient calculated using second order Fichtean diffusion equations. So you can see that there's quite a bit of improvement. Even some of them were tremendous improvements, and then some of them were less. It greatly depends on the concrete, the parent concrete. How permeable is that concrete? How reactive is that concrete? So my suggestion is that what the research has shown is it's going to improve permeability characteristics. It's going to improve compressive strength characteristics. It's going to decrease shrinkage. But to what degree, it's going to do it to a certain minimum amount, but to what degree is dependent upon the raw materials. Like so many questions with concrete. When we we talk about concrete technology, one of the first things I tell my students at the school is, just because a concrete mix design works in Chattanooga, Tennessee, doesn't mean that it's going to work in Atlanta, Georgia, or doesn't mean it's going to work in Dubai, UAE, because the raw materials are fundamentally different. And that's why folks like me have a job, is because there's so many variables that it's very difficult to track all those variables. And the best that we can do is to try to have predictive models that will tell us how the concrete is likely to behave. So when we have colloidal nanosilica being applied to concrete, my suggestion is to always, if there are general contractors, engineers in the room, my suggestion is to try it on concrete made with raw materials that are going to be used on the project and do the testing to see what the effects will be with that particular raw material combination. This is just a continuation of the previous slide. You can see more improvements on permeability. Since this was done, I've since begun running some permeability testing using a new test standard called, or it's new to me, it's not that new, NT492, NordTest 492. Does anybody have any experience with NT492 in the room? Right, NT492 is a very fast electrostatic way to pull chlorides into the concrete. So you have calcium hydroxide on one side, sodium hydroxide on one side, sodium chloride, salt water on the other side. You induce a voltage, and then you can pull chlorides into the concrete and then measure the chlorides and how quickly. So it makes a comparison between untreated concrete and treated concrete with colloidal nanosilica. It makes it very fast and very easy to determine how well the concrete's going to improve. Here's a slide from a DIN 1048 test. So I did say that we did a lot of ponding tests on permeability, but we also ran some DIN 1048, which that's a European standard. This sample here, this was a particularly bad concrete with a water cement ratio of up around 0.60 or so. And this test here, let's see if I can figure out the pointer. This is a penny, US penny. This test here was stopped after only 20 minutes because the water was going through the concrete sample so quickly that they shut the test down. This was 72 hours, same concrete, the only difference being that this was treated with spray applied colloidal nanosilica. 72 hours, there was only about 5 millimeters of penetration into the concrete. That's a pretty significant change in how that concrete was behaving. So this testing was done under hydrostatic pressure. The DIN 1048 test puts about you can set it at different pressures, but I think we ran it at 7 bar. Just to give you an idea of how the concrete will behave under hydrostatic pressure. And you can see the improvements have been significant. And of course I did not do these tests here. This was done in previous laboratories. But you can see on up to here, DIN 1048. This is U.S. Army Corps of Engineers hydrostatic test. So all of these are DIN 1048 except for these. The only difference between the tests is that these are using pneumatic air to apply water pressure. So you have water and air pressure behind it. And this is using, the Army Corps of Engineers requires you to actually have a 100-foot column and drop the water into the concrete. So we're simulating, this is simulating the water column, and this is actually using the water column. So the average of all these tests is a 76% improvement in hydrostatic pressure resistance. Standard deviation of about 13%. So what does all this mean? If the colloidal nanosilica improves permeability of the concrete to this degree, how does it relate to how long the concrete is going to last? Some of you may have heard of Life 365, possibly in the room. Life 365 was a corrosion modeling software project several years ago. It was undertaken by the American Concrete Institute, or ACI, Committee 365. They did it in combination with the American NIST, or National Institute of Standards and Technology, along with ASTM, the American Society of Testing Materials. And they put a lot of work into this to develop a conservative life expectancy model to try to get an indication of how long concrete would last, reinforced concrete would last, under chloride loading at various concentrations with various permeabilities. So the general idea behind it is that as permeability changes, permeability of the concrete changes, then chlorides will reach the rebar, or reinforcing steel, based on the diffusion coefficient at different times. So if the chlorides reach the reinforcing steel earlier, then the chloride corrosion begins earlier. The life cycle of the concrete is reduced with higher permeability. As the chloride diffusion coefficient is smaller, then it takes longer for those chlorides to reach the reinforcing steel, and the concrete will last longer. So we've begun using Life 365 to estimate gains in service life of concrete treated with a colloidal nanosilica. And we can see, it's kind of hard to see, and I apologize for that, but the next page will give you an idea. I'm going to go through just a few of the model ideas behind the model here. You set your rebar depth, your reinforcing steel depth, and the amount of cover. And then you have the depth of the entire concrete placement. This is done in a one dimension here. You can set it up in 2 dimensions or 3 dimensions. You set your surface concentration. There are defaults in the system, so if you want to do a parking deck in New York City, then you can do a parking deck in New York City, and it makes some assumptions that de-icing salts are coming in on the car wheels and those kind of things. So there are some defaults in there that you can use if you choose, or you can set it up with your own constraints. Monthly temperatures are also fed into the model. This is a probabilistic model. So what it means is that statistically, thousands and thousands and thousands of cases have been fed into this model to train it, to tell it when corrosion is going to most likely begin to occur. So I'd invite you to take a look at Life 365 and read the background of how they developed the model and how it performs and what it means. I'm not an expert on how it does it. I just have learned to use the model to help me estimate how long concrete will last. So we can see on this particular model, we used a 0.35 plain cement mix, plain Portland cement mix, no supplementary cementitious material. That was our base mix. I'll go ahead and change to the next page. So 100% cement, no supplementary cementitious material. The models predicted that the service life of that concrete was 20 years. 20-year concrete, I don't know too many engineers or owners that would be happy with concrete that was only expected to last 20 years. So the next thing that we did is we took a spray-applied colloidal nanosilica to this 100% cement concrete with no pozzolans, and we were able to extend the lifespan up to close to 30 years. So we gained 10 years, or a third roughly, by applying colloidal nanosilica. We used the chloride diffusion coefficients that I showed you earlier from the ponding test that we had. So we took an average from those, and we were able to reduce our permeability, and which extended the lifespan. So then we looked at 100% cement plus a spray-applied colloidal nanosilica and an integral admixture colloidal nanosilica. So we've been testing integral admixture colloidal nanosilica along with the spray-applied the whole time. And we can see that the two complement each other very, very nicely. So instead of having a 20-year lifespan, now we're up above 40 years. So we've doubled the lifespan, or even 2.5 times the expected lifespan. By reducing that diffusion coefficient of chlorides, we're keeping those chlorides away from the steel and making the concrete last longer. So the next case we looked at was a 25% fly ash mix. Fly ash, for those of you that may not be familiar with the term, fly ash is a byproduct of the coal burning industry for electric power generation. So I didn't really repeat that. I just I wanted to do the spray only and then a combination of the two. Yes, sir.
What's the percentage we talk about in that substance?
The percentage in here is, this was a liquid admixture, the integral was a liquid admixture done at about, I'm thinking in US units, about 1.2%. About 1.2% there. Now the spray applied is a little difficult to assign a percentage because you're spraying it and it depends on the porosity. So we did not, in a future study, I would like to weigh the samples before, weigh them after, and then I would have an idea of how much it absorbed. But for this study, I did not do that.
When you say it's applied in liquid form, I mean, is it liquid form slurry form or is liquid?
It's not. It's a very low viscosity spray.
Oh, right.
Yeah. So it's and it's very small particle sizes, so it's able to penetrate deeply into the concrete. And that's the other thing we'll get to in a moment is the actual application of the material. I'll get into that and explain that in a little more detail.
Any idea on the specific gravity of the liquid material?
The specific gravity of the material itself, it's about 1.1. So, all right, we'll continue. There'll be a time for other questions at the end. So if you'd like to put a bookmark there, then we'll continue on. So we had a case study in Port-à-Marseille, France. They had a test case that they wanted to try, a 70-meter long sporting quay, or sporting, I think my Australian friends will make fun of me how I say quay. We say quay in the US, I don't know what you guys say, but so it's a boat dock. And the Port Authority wanted to try spray applied CNS to reduce the permeability and attempt to reduce the number of contraction joints. They had seen the research and they saw that it could reduce shrinkage. So I recommended, from a stress analysis, I recommended that they reduce the number of joints from 7 to 3. But the Port Authority called me a couple of weeks after they placed it, and they said, Brent, we placed your concrete. And I said, okay, how did it go? And they said, well, it went great. We don't have any cracks. I said, well, how many joints did you cut? He said, we didn't cut any. I said, you got to be kidding me. Yeah, then you got lucky. Okay. Spray applied colloidal nanosilica is not the golden prize for crack-free concrete, but it will greatly reduce the chances of dry shrinkage cracking occurring. You can move joints out further. How far, you might ask? Well, again, it's going to depend on the specifics for the project. It's going to depend on how permeable the concrete is, what the aggregate package is. There's so many variables, but it is something that we can that I can kind of have an idea of about how much, just from a mixed design analysis, and an idea of how the substrate of the concrete is going to react with the concrete itself and those kind of things. So I did get lucky. It made me look like a hero to the Port Authority, but it was more luck than anything. I asked them to do 3 and they did 0. So the application of the spray applied, the application is relatively easy. The particular product that we were working with was a zero VOC product, so there was no danger to the environment or anything like that. And basically the way that they apply, and the greatest success that they've had, is to apply to rejection. So they spray the colloidal nanosilica and then they wait a few minutes and see if it disappears. And if it disappears, then it's being absorbed in the concrete. They apply again immediately. So it's only, there's a 15-minute window, excuse me, so they repeat 2 to 3 applications during this 15-minute window until it ponds on the surface after that 15-minute window. And then they know they have maximum penetration of the colloidal nanosilica into the concrete. And that seems to be when it works well. When I first heard about the product, one of the first tests that I did was I took a pan in my laboratory and I put some of this colloidal nanosilica stuff in the bottom of the pan, this liquid. And I took an old concrete cylinder that I had sitting in the lab for a year or so. and in the liquid. Went back to my office, did some work for Dr. Wino. My boss is here from UTC, making sure that I'm actually presenting here in Dubai, that I'm not off party. So I'm doing some work, and I go back into the laboratory an hour or so later, and I see that the material has actually been wicked up into the concrete vertically. It pulled the product into the concrete vertically. That's when I told myself, hey, this is different. This is something that could be potentially an innovation. Let's see what we have here. And sure enough, it can actually be applied on vertical surfaces, walls, as well as ceilings. There's an ionic attraction that's going on there. It's the way it's been explained to me. I'm not a chemist, but it's chemically attracting the product into the capillary void system. I've actually seen with my own eyes it displace materials that are in the capillary voids. Did a project, it's not detailed here, I apologize, but we did a project where we took some salt, introduced sodium chloride into concrete on purpose, 5% by volume. We treated with colloidal silica just to see what would happen. We were running half cell potentials on some rebar that I embedded in the beams. Came back the next day, and I had a concrete beam that had white fuzz on it, about that thick, I don't know, 6, 7, 8 millimeters thick. You could write your name in it with your finger. And I called the guy that was sponsoring the research. I called him over. I said, you got to come look at this. And he came over and he said, well, Brent, what is it? And I said, it's salt. We mix salt into this concrete, it's purging salt out of it. He said, there's no way. I said, yeah, it is. He goes, well, how do you know? So I went, that's salt. So probably shouldn't have done that, but I've been around concrete my whole life, and I knew there wasn't anything that was really going to hurt me. So, but yeah, we've actually seen it displace things in the capillary void structure. It's preferentially, it's preferred because of that ionic attraction. It gets pulled into those capillary voids. The reaction begins to happen, and it's making calcium silicate hydrate. As it makes that calcium silicate hydrate, it's pushing anything else that's in that void system out. So I've seen on job sites that the company that was sponsoring the research, I've seen on job sites, they called me up. I've seen red line purged from a pool deck. I've seen some interesting things happen. So the penetration depth depends on the permeability of the concrete as well. We talked about so many things depending on the substrate permeability. But we've seen in the laboratory, as well as cores taken from the field, typically somewhere between 50 and 300 millimeters is how deeply the product will go. It depends on the water cement ratio. Again, permeability has so many variables. In some cases, shotcrete applications, we have seen as much as 250, 300 millimeters. So that's mostly a very permeable shotcrete applications at the higher level. But 50 to 150 is normal. We'll see 50 to 150 millimeter penetration on many of the samples. So, in conclusion, I think that we've shown that the academic literature is now understanding, the academic researchers out there are understanding that colloidal nanosilica may be something special. That it may be something that can help us with concrete durability. And our testing at the laboratory at UTC has confirmed a lot of that previous work, but also we've seen some things that some of the other researchers hadn't seen yet. But finally, the test cases, which include the Port of Marseille, as well as others now that have been done, has demonstrated that it's an easy product to apply, and that it's effective. When we saw 0 cracks on the Port of Marseille boat dock, we got lucky, but at the same time, if it hadn't been there, I'm confident there would have been some random cracking. So that wraps up the presentation.